Question 3. A. A and B reacts to give the product AB. When the concentration of A and B are both 0.1 mole per dm cube, the rates of the formations of AB is 7.62 times 10 power negative 4. So when the concentration of A and B now both increases and is double, from 0.01 now increase to 0.02. So both A and B now concentrations double. The rates of the formations of AB now is increases. The first thing that you need to do is compare the rates. So the one with 0.01 mole per dm cube, so compare with the one that 0.02. So we know that the rate now is increased 4 times. So from this to this, so it's increased 4 times. Now the concentration of the A and B both double, and the rates increase 4 times. So there are a few possibilities. So it could be the A is in first order, B also first order. So means when the concentration of A and B both double, so you get 4 times. Or it could be just the A is second order. So means when this concentration double, so it will increase 4 times as well. Means the orders for B is 0 order. So means it's 1, right? And or it can be the B is second order. So when the concentration of B double, the rate also is 4 times. So means these are the possibilities that it could be. It could be both reactants first order, or only A second order and B second order. So this is the one that you must compare. Now part 2. Choose one of the rate equations you have written in the part 1 and calculate the values of the rate constant including the unit. We just use the first one. So the rate is equal to K times the concentration of A and concentration of B. So because the concentration already given, both A and B, they are 0.02. So we just use 0.02 times 0.02. Okay, so this is a K we need to find. And this is the rates for the higher concentration here, right? So then rearrange, you should get 7.625. The unit is very easy because the rates here is mole per dm. This one is mole per dm cube per second. So both of this concentration is mole per dm cube. So this is how you find the unit. You just cancel out each other. So at the end you get per mole dm cube per second. Part 3. Explain why it is not possible to calculate the value for the half-life of this reaction using the value of the rate constant calculated in this part 2. And the equation is this one. Okay, it's not possible to use this equation to calculate the values. Why? Because the half-life, okay, this is the formula or the equations for the first order. So in this question, the equations that are given here, which used to calculate half-life, is for first order only. So as you can see, the reaction is overall is actually second order. Okay, either it's 1 plus 1 or okay, this second order for any one of these reactant. So therefore, okay, because these equations that given is for the first order, so we cannot use this equation to get the half-life. So answer is very easy because the reaction is second order. You cannot use the first order equations to calculate the half-life. Okay, there is another one, but in this A-level syllabus, you no need to know others equations. Means you just need to know the equations for this first order. The second order, zero order, you no need to know the equation. Part B. Catalyst may be homogeneous or heterogeneous. Part 1. Identify two metals that act as a heterogeneous catalyst in the removal of nitrogen dioxide from the exhaust gas of car engine. So there are three metals. So you can actually get this from the periodic table. No worry, you no need to memorize the name. You can get it from the periodic table. Just roughly know where are they, right? So they are platinum, palladium, and rhodium. Remember, these are the three metals that stated in your syllabus is used for the removal of this NO2 in the car engine exhaust. Part 2. Iron act as a heterogeneous catalyst in the Haber process. Describe the mode of action of the ion. Heterogeneous catalyst is quite straightforward. Ion catalyst and the others heterogeneous catalyst or metal catalyst is actually similar. So if you involve three process, okay, the first one is the adsorption. The reactants will adsorb on the catalyst surface. Once it's adsorbed on the catalyst surface, so first actually it will undergo bond breaks, or the bonds get weakened. Second, then it will form the bonds or the chemical bonds between the reactants or the atoms. First it will be adsorption of reactants, and there will be a chemical bonds formed between catalyst surface and the reactant. So then the bond will get weakened, and there will be a reactions between the atoms and the bonds formations in products. Actually, you can make it more specific. You can put the adsorptions of the nitrogen and the hydrogen gas on the catalyst surface. Then the N triple bond and the HH bond will get weakened, and there will be a reactions between the nitrogen and hydrogen atoms, and they will form products. Obviously, the products is ammonia. Once they form the ammonia or the products, and this ammonia will undergo desorption. So the chemical bond between the products and the catalyst will break, and these products will form. So these are the action mode of actions for these metal catalysts. So you can follow the mark scheme, make it as general like this, or you can actually give the specifics explanation, involve the gases like nitrogens and hydrogens, as I told you just now. Part 3. Iron 2 ions act as homogeneous catalysts in the reactions between the iodide and peroxide disulfide. Write equations for the two reactions that occur when iron 2 is added to the mixture of iodide and peroxide disulfide. This is very specific. So because it stated iron 2 added to the mixture, means it must start from the iron 2. So iron 2, we know that after it reacts, it will form iron 3. So means it will get oxidized. So means the species that undergo reduction will react with the iron 2. So in this reaction, the peroxide disulfate will get reduced. It will reduce to this sulfate. So means you need to put the iron 2 together with peroxide disulfate. Iron 2 will oxidize to iron 3, and this peroxide disulfate will reduce to the sulfate. Then you just balance it, put all 2 here. Next, after the iron 3 produced, then the iron 3 will further react with the iodide. Iodide, we know that it must undergo oxidation. It must oxidize, form iodine. So means now the iron 3 will get reduced to iron 2. At the same time, it's oxidized the iodides to form iodine. So the iron 2 now regenerate. Use back for the first equation. That's why we say iron 2 is a homogeneous catalyst, because it can be regenerated. Part 4. Explain the difference between a homogeneous catalyst and a heterogeneous catalyst. Okay, so this one is very easy. Homogeneous means the catalyst is in the same phase with the reactants. Like gas, then they are all gas. So heterogeneous means it must be different phase. Like reactant is gas and the catalyst is a solid. Right? So heterogeneous catalyst is in the different phase with the reactant. That's all. Now part C. Iron 2 can be oxidized to iron 3 under alkaline conditions by suitable oxidizing agent. Okay, part 1. Iron is a transition element. Explain why iron forms stable compounds in both positive 2 and positive 3 oxidation states. Okay, so it must be a reason why it's always form positive 2 and positive 3. First, of course, in the mark scheme, you see this one. Because there is a similar energies of 3D subshell and 4s subshell. It's true. Before the iron is get oxidized, release electron. So the electrons must release from the 4s subshell. Why? Because the 4s subshell is higher energies levels than 3D, but it's not going to higher that much, slightly higher. So these 2 electrons will release, and eventually it will form iron 2. After that, iron 2 will easily release another electrons here, 3d6, another electron here. Once it's released the electrons, it will form the 3d5. 3d5 is quite stable because it's half-filled configuration. So therefore, this iron 3, it will be a stable form for this iron iron metals, right? Okay, so this is the reason why it's always able to form these stable compounds of positive 2 and positive 3, because their energy level is very close. Very easy to release the 2 electrons and another electrons from 3D from the 2 oxidation states. Okay, part 2. The half equations for the reduction of iron 3 under alkaline condition and is this electropotential are shown. This is a standard electropotential in NOT. Okay, this is the one. Iron's 3 hydroxide gains electrons to form iron 2 hydroxide, okay, plus the hydroxide. Now, 4 more half equations for the reactions under alkaline conditions given. And now the question is what? Select 2 oxidizing agents that can oxidize iron 2 to iron 3 under alkaline condition. Okay, oxidizing agent means itself must get reduced. And first, we need to make sure this iron 2 will get oxidized and form iron 3. Means this equation must reverse. This equation must reverse. Means the iron 2 now, okay, after it's reversed, it will release electron and get oxidized. Means from these 4 equations, you need to find the E0 which is more positive than this one. Why? Because when the E0 is more positive, so they are more likely to gain electron from this half cell. So obviously, okay, they are the second one and the third one. So because it's 0.89 volt and 0.4 volt, right? So this one and this one, okay, is larger than negative 0.56. Okay, the first one and last one cannot. Okay, so once we know that, so we can construct the equations already. So the first equation, before the equations, we need to state the oxidizing agent. Okay, if let's say now we choose this one, right? So the oxidizing agent is very obvious. Okay, so you see this is the correct. Now it's from correct. So it's from, okay, this one is -2. Okay, this is -2. Overall is negative, so it must be +1. So +1 to -1. So it's undergo reduction. So means this is the one that oxidize the iron 2. So you just need to put the correct ion here. So how to get the equation? Very easy. So the first one here, this one, okay, the second equation, just stay. So means let this one as in reduction form, like this, and these half equations reverse. So you get this. Okay, so this one stay, and this is a reverse equation. After that, we need to make sure the electrons number same. So this equation here, we need to times 2. Then we can cancel out the electrons. So you get this. Okay, so now sum up these two equations. Okay, so this one cut. Okay, hydroxide is cut, and you just sum up left to left, right to right. So you get this equation. Okay, so means sum up this one, and you sum up this one. So you get the equation. So last part is calculate the E0 cell. Very easy. You just use the cathode minus anode. So therefore, we know that this one that stay in reduction form, okay, because they gains electron, they are cathode. So this one, because it's reverse and release electron, this is anode. So you need to use the cathode minus anode. So use 0.89 minus negative 0.56. So you get this 1.45. For the second oxidizing agent, this one you just follow the same way. So the oxidizing agent for the third equations here, obviously is oxygen. So it gains electrons and form this hydroxide, right? So you just put oxygens as oxidizing agent, and after that you need to form the equation. So because here there are 4 electrons, so this equation now you need to times 4. So let this one stay and this one reverse times 4. You get this. So this one same. So this one already reverse times 4. Okay, then you sum it up. Cut the electron first. Hydroxide cut. Okay, then sum up left to left, right to right. So this one only one species. So you get this equation. So calculate the E cell. Again, use cathode minus anode. So use 0.4 minus negative 0.56. So you get 0.96. Okay, that's all. Thank you.